Okay. Okay. Okay, so last exercise that we did was exercise 78. So let's do exercise 79. So it's a refer to the exhibit. What will the router do with a packet that has a destination IP address of 192.168.12.27? So a router, when it have a packet, it receives a packet, it have to take a decision where to forward the packet. So a router has several interfaces. So it receives on one interface and forward it to another interface. So the packet finally at one point will arrive to the destination, no? So for that, it will check the routing table. The routing table has several entries. For example, this routing table have 1, 2, 3C, and 1S. So there are 4 entries. So the router is going to ask first, is this IP address in, for example, this entry, the first entry, which appears with a S, which is 0.0.0.0//0. So this is the default route. All IP addresses are always inside. So this IP address, of course, is inside. So this is a hit. Since it is a hit, it's the first possible solution. So the router continues. It say, oh, I have another entry here. Is this IP address is in this network? The 192.168.10.0/24. Yes or no?
No.
No, thank you. Because all the IP address in this network start with 192.168.10. So this one starts with 192.168.12. It cannot be here. So this is a fail. So we still have just one candidate, the first one. So let's go to the third possibility. Here we have 192.168.11.0/24. So is this IP address belong to 192.168.11.0/24? No. Okay, because all the IP addresses that belong to this network start with 192.168.11. This one starts with 192.168.12. Doesn't belong. So this is a fail. And there is a last possible case. Is this IP address is 209.168.200.224/30? No. So at the end of the 4 possibility, there is only one hit. One hit and 3 fail. So there is only one possibility, and this possibility say, send the IP address to the next hop, which is 209.165.200.226. So the router always need the exit interface, the outgoing interface. It's going to send the packet out, so it needs to determine the interface. Here, we did not specify the outgoing interface. So the router is going to do a second search in the routing table to find the outgoing interface. So this hit says send it to 209.165.200.226. So now the router asks himself, if I want to send a packet to this IP address, what should I do? So it's do a second search with this IP address this time. So is this IP address in this network?
Zeros. No.
Yeah, it is.
Yes.
So yeah, okay, so it is a hit. So first hit. So let's go to the second. Is this IP address is in the second network, the 192.168.10.0/24? No. So we still have just one. Is this IP address, the 209.165.200.226, is in this network? No. The 192.168.11.0/24? No. Is this IP address in this network, the 209.165.200.224? Yes. In this network, we have 4 IP addresses. the 224, the 225, the 226 that we are looking for, and the 227. Remember that 224 and 227, we cannot use them. 225 and 226, we can use them. So there is a hit here, and there is a hit here. We have two hits. So when we have several hits, the router will take the network that is more specific, which means that is smaller, that have less IP addresses. How many IP addresses we have here? 4. How many IP addresses? Because we have two hits, a hit here and a hit here, to find this IP address. Here we have 4 IP addresses. How many IP addresses we have here?
All.
All. Exactly. All the internet is there, which is 2 to the 32. All the IP addresses of the world are there. So which one is smaller? The one that have 4 IP addresses or the one that have all IP addresses? This one is smaller. So it will do what we have here. And look at what we have here. It says send it out to serial 000. So after 2 search, the router finally know what to do. It will send it out this interface, the serial 000, to the next hop, which is 209, 165, 200, 226. So let's see the possibility that we have here. A, drop the packet. So no, it will not drop the packet. It's going to process it, okay? So send the packet out serial 000. That's true. It will send it out 000 to the next hop 209, 165, 200, 226. Let's see the other possibility. Send the packet out gigabit Ethernet 0/0 interface. No. And send the packet out the interface gigabit Ethernet 0/1. No. So these two are not correct, no? Okay. Is it okay for everybody? So let's see next exercise, which is very similar. So they say refer to the exhibit. R1 receive a packet destined for the IP address 192.168.210. At which interface will R1 forward the packet? So the same process. How many entries we have here? So the only entry that we will not take into account are the entries that appear with L. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we need to compare this IP address with the 9 possibility. So let's see. 192.168.210 belong to this network. 192.168.10.0/24. No. So this is a fail. Now, is this IP address belong to 172.16.11.0/24?
No.
No. Another fail. Is this IP address belong to 172.16.1.0/24? No. Another fail. Is this IP address belong to 10.10.1.0/24? No.
No.
Another fail. So is this IP address belong to 10.3.3.0/24? No.
No.
Is this IP address belong to 10.1.0.0/16? No. Another fail. Is this IP address belong to 192.168.1.0/24? No.
No.
Because the IP address that belongs to this network, the first 24 bits must be 192.168.1. This one is 192.168.2. So it doesn't belong to this network. Another fail. So is this IP address belong to this network? 192.168.204/24? Yes. So this is a hit. This is the first hit. Let's keep going. We don't stop with the first hit. So is this IP address belong to 192.168.304/24? No.
No.
So we have only one hit, and this hit say what? Send it to this next hop, and this next hop is 172.16.12. Okay. So we need the output interface. We know what is the next hop is 172.16.12. So we make a second search to know if we want to reach 172.16.12 as an intermediate step toward the destination, which is 192, the final destination, which is 192.168.210. What should we do? So we make a second search for this IP address this time. So is 172.16.12 in this first network?
No.
No. Is it in 172.16.11.0? No. Is it in 172.16.104/24? Yes.
Yes.
So here we have a hit. So we keep going. We have one hit for now. This one will be a fail, okay? This one will be a fail. This one will be a fail. This one will be a fail also. This one will be a fail. This one will be a fail. So at the end, there is only one hit for looking at this IP address, no? And the hit is this. The hit say, send it out serial 001. So I will send it to 172.16.12 out of serial 001. So the answer is this one. It will send it out this interface after two search. So the router, sometimes there is enough information, and with the first search, have all the information that it needs. It does need the output interface or the outgoing interface. So if with the first search, it doesn't have the outgoing interface, it has to make a second search to get the outgoing interface. Because of course, if I'm a router, I have several interfaces, I have to forward a packet, I need to know through which interface I'm going to send the packet out, which is the outgoing interface, no? Question 81, refer to the exhibit. Host A is attempting to contact server B. Which two statements correctly describe the addressing that host A will generate in this process? Choose two options. So a packet with the destination IP address of router B. So if if host A sends something to server B, will the destination IP address will be the one IP address of router B?
No.
No. What can we say about this packet that A is going to send it to router A? This will be the first hop. Remember, this is a transparent switch. Then router A is going to send it to router B. Then router B will send it to server B. This is a transparent bit. So there will be three hops. First hop, second hop, third hop. Remember that the IP address does not change, which means that since A create the packet, what will be the source IP address?
Host A.
Exactly, it will be the IP address of host A. What will be the destination IP address?
Server B.
Correct, it will be the server B. So in the three hop, the IP address is the same. The source IP address and the destination IP address. Now what will change is the layer 2 information. Remember that the layer 2 is local to the link. So in the first hop, we are using Ethernet. So we will have MAC addresses. In the first hop, what will be the destination MAC address?
Router A.
Router A in this interface, okay? Because router A has several interfaces. So in this interface, it has a MAC address. So in the first hop, the destination MAC address will be the MAC address of router A in this interface. What will be the source MAC address?
Host A.
Correct. The MAC address of host A. Let's talk about the last hop, the third hop. In this hop, what will be the destination MAC address?
Server B.
Server B, correct. It will be the MAC address of server B. What will be the source MAC address in this hop?
Router B.
The MAC address of router B in this interface, okay? Now, if I talk about, this is one technology, wide area network technology. This is serial links. Here, we also have layer 2 addresses, but they are not called MAC addresses. So it will depend on the encapsulation that I put. On a serial link, I have to choose my encapsulation. Cisco router by default use HDLC, but you can change it to PPP, point-to-point protocol. You can change it to frame relay, okay? So according to the encapsulation that you choose, you will have different name for the layer 2 address. For example, in frame relay, it is called DELC. Okay, so let's answer now this question. The packet with the destination IP address of router B now. The destination address will be router A in this interface. A frame with a destination MAC address of switch A. The router on the PC doesn't even see that there is a switch. It's totally transparent. So no information of the switch is included in this because we don't see it. Okay? So a packet with a destination IP address of router A, of course, it will not be that because at the level of IP addresses, it doesn't change. So it will be the source IP address will be host A and the destination IP address will be server B. So that's not the correct answer. A frame with a destination MAC address of router A. Yes. So this one will be correct, no? Router A in this interface. A packet with a destination IP address of server B. Correct. And a frame with a destination MAC address of server B. No. Okay? The MAC address of server B here should never be mentioned because MAC addresses are local to the LAN. So for example, the MAC address of A in this LAN is something that we can talk about it. But the MAC address of A here, we should never talk about it. Never. The MAC address of A stay here. Because in layer 2, we are inside a local area network or inside a link. So we never talk about the MAC address of A here, of host A on this side. Never, never, never. Okay, question 82. Refer to the exhibit. Which statement describe the media access control method that we use, that are used by the networks in the exhibit? So look at here. We have a LAN, which is Ethernet. Here we have a WAN. Okay, so it's a serial link. So we might use different encapsulation. And here we have Wi-Fi. We have a wireless connection. Okay, so they say all three networks use carrier sense multiple access with collision avoidance. Where do we use this method? in wireless technology. So this is the method to access the medium when we use wireless technology. So here, we'll use carrier sense multiple access with collision avoidance. If you remember when we saw that, I told you that we use collision avoidance because it's very difficult in wireless technology to detect a collision. So what we try to do, we try to avoid collisions because we cannot detect them. Ethernet can detect them and don't have problem to detect them. But Wi-Fi do have problem to detect them. So we try to avoid them. So here we will use carrier sense multiple access with collision avoidance. So none of the network require media access control. Of course, all the network need one. Okay, because the medium is shared. And only one station can transmit to the medium at a time. So we need a way to control who is going to transmit. Okay, network one, which is this network, use carrier sense multiple access with collision detection. And network three, which is this network, use carrier sense multiple access with collision avoidance. This is true. Okay, Ethernet use carrier access multiple access with collision detection. In Ethernet, I'm able to detect collision. So I transmit. First, in Ethernet, what should I do if I need to transmit? I listen the medium to see if there is activity. If there is already a station that is using the medium and is transmitting, I cannot transmit. I have to wait the end of the transmission of this station and then try to transmit. But I cannot transmit if another station is already transmitting. Now, if I listen and there is no activity, I can decide to transmit. But when I transmit, I also listen what I'm transmitting. If I see a difference between what I'm transmitting and what I'm listening, it's because there were a collision. So two stations, me and another station, decide to transmit at the same time. And of course, the signal of both stations add up, and the signal is different from what I'm transmitting. So I'm detecting the collision. In this case, all the stations that are transmitting stop transmitting. And at the beginning, they take a random number between 0 and 1. So if, let's say that two stations was involved in the collision. If both have 0, what does it mean? If both, when they take their random number, take 0. That means that they have to wait 0 period of time to retransmit. So they can retransmit right away, both of them. If this happens, we will have another collision. If both of them take 1, what does it mean? Both of them have to wait 1 period of time before retransmitting. So both of them wait 1 period of time, they retransmit at the same time, another collision. Now, if one, when they take the random number, takes 0, and the other one take 1, what does it mean? The first station that have 0 don't have to wait. They have to wait 0 period of time. The other station that have 1 have to wait 1 period of time. So what will happen? The station that have 0 start transmitting. On the other one, when the timer time out, it will see that the first station already is transmitting, so it will have to wait. So in this case, we don't have collision. So if we did have a collision again, because both got 0 or both got 1, what will happen? They take random number between 0 and 3. So 0, 1, 2, 3. If both take the same random number, let's say both take 2, what will happen? Both have to wait 2 periods of time. And after 2 periods of time, they transmit at the same time, there is another collision. So they will take random number between 0 and 7. Now, if when they took random number between 0 and 3, one took 1, and the other took 3, if they took different random number, there will be no collision. Let's say that I took 1 and the other station took 3. I wait 1 period of time and I start transmitting. When the timeout of the other station is done, if I'm still transmitting, the station will realize that I'm transmitting, and she will have to wait. It will have to wait. So there is no collision if we have 2 different numbers. So we go with numbers that are bigger to try to avoid a collision. Because if the interval where we select the random number is bigger, the probability that we take the 2 stations take the same random number is smaller because the interval is bigger. So we try to avoid a second collision or a third collision or a fourth collision, no? This is carrier sense multiple access with collision detection. So Wi-Fi is different. Wi-Fi cannot detect collision easily. So Wi-Fi, what it does, Ethernet don't have acknowledgement. So if I'm a Wi-Fi station, like this laptop, and I want to transmit, first I listen the medium. If there is activity, I cannot transmit. I have to wait. If there is no activity, I can decide to transmit. So let's say I transmit, and I wait for an acknowledgement. If I don't receive an acknowledgement, it means that my transmission got involved in a collision. It's difficult for me to detect the collision. So it's why I rely on an ACK. So Wi-Fi rely on ACK. Ethernet, no. Ethernet send the frame and listen. If what I'm sending is the same as what I am listening, there is no collision, and I assume that the destination get the frame. Wi-Fi is different. Wi-Fi don't listen when it's sending. It sends and wait for an ACK. If I receive an ACK, bingo, it was successful. So it's why Wi-Fi use carrier sense multiple access with collision avoidance, no? Okay, let's see. Network 1 use carrier sense multiple access with collision avoidance. That's not true. Ethernet don't use collision avoidance. Ethernet use collision detection. Network 2, this network, use carrier sense multiple access with collision avoidance. That's not true. Network 2 will not have problem of collision normally. Or yeah, it might have, but they don't use this method of access, are not used in serial links. Okay, carrier sense multiple access collision detection is Ethernet, and collision avoidance is Wi-Fi, is a wireless network, no? Question 83. What are 2 characteristics of 802.11 wireless network, which is Wi-Fi? Choose 2 options. So they use this technology. This is true. They use carrier sense multiple access with collision detection. This is not true. This is Ethernet. They are collision-free network. They do have collision, but it's very difficult to detect the collision. Station can transmit at any time. That's not true. Because before I transmit, I do listen the medium to see if there is activity. If there is activity, I cannot transmit. So collision can exist in the network. Of course, we do have collision. They are difficult to detect, but we do have collision. Okay. Oh, this is a nice one, but I'm going to skip it for now because I want to do other exercises before we can do 84. We can come back to it. Okay, 85. Refer to the exhibit. So they say, A, if the port of the switches, we have a switch here and we have a switch here. Those are hub. If the port of the switches were half duplex, what will be the number of collision domain? So what do you think? So if my port is half duplex, this port is half duplex in switch 1. This port is half duplex. This port is half duplex. What does it mean? That here, between switch 1 and switch 2, we can have collision. So this will be a collision domain between switch 1 and switch 2, which means that since there is only one pair of wire, this is a UTP cable. It has 4 pair of wire, but of the 4 pair of wire, we use the same pair of wire to send and receive. So if switch 1 decide to send something to switch 2, at the same time as switch 2 decide to send something to switch 1, since they use the same pair of wire, we will have a collision between switch 1 and switch 2. But this collision will not be propagated outside this link. So this will be one collision domain. Okay? Which means that between switch 1 and switch 2 here, only one can transmit at the time. Now we will have another collision domain here. It will include the 3PC and this interface of the switch. This is a hub. A hub, the whole hub is one collision domain, which means that all the devices that you connect to a hub, only one can transmit at a time. Why? Because the hub always do flooding, which means that if this PC sends something to the hub will copy it to this PC, and to the switch. So let's try to see if this PC and this PC can transmit at the same time. So let's say this PC is transmitting and this PC is transmitting. So because this PC is transmitting, the hub will copy it to this PC. And there will be a collision because this PC is also transmitting. So these two cannot be transmitting at the same time. Now, can the switch be transmitting at the same time as this PC? What will happen? If the switch transmits, the hub always copy it to everybody. So it will copy it to this PC, to this PC, to this PC. So if this PC is also transmitting, there will be a collision because what the switch is transmitting will be copied to this PC, to this PC, to this PC, and this PC is transmitting, so there will be a collision. So between this interface of the switch and this 3PC, only one at a time can transmit, which means that this interface on this 3PC are another collision domain. In a collision domain, all the devices that are connecting, only one can transmit at a time. Here we will have a third collision domain. It will include this interface and this 3PC. Here we will have a fourth collision domain. It will include this interface of switch 2 and this 3PC. And here we'll have a fifth collision domain. This interface of switch 2 and this 3PC, which means that maximum in this network, we can have 5 transmissions in parallel, not more. So for example, this PC can be transmitting at the same time this PC is transmitting. At the same time, for example, this PC is transmitting, this PC is transmitting, and switch 1 is sending something to switch 2. No more can happen. If these two PC transmit at the same time, there is a collision. If this PC and switch 2 transmit on this interface at the same time, there is a collision. So one collision domain, it includes this interface of switch 1, this interface of switch 2, a second collision domain, this interface of switch 1 and this 3PC, a third collision domain, a fourth collision domain, and a fifth collision domain. So 5 collision domains. Okay, let's see B. If the port of the switch are half duplex, what is the number of broadcast domain? Oh, now it's broadcast domain. So a whole hub is only one broadcast domain, and a whole switch is only one broadcast domain. In which case I will have several broadcast domains, only if I have router. Each interface of a router will be a different broadcast domain. So here, that will be just one broadcast domain, which means that if this PC sends a broadcast, all the other PC will receive it. If this PC sends a broadcast, all the other PC that are here and here will receive it. There is only one broadcast domain. Okay, let's see now. If the port of the switch are full duplex, which means that we have bought some switches that are new, not the old one. What is the number of collision domains? So this port is full duplex, this port is full duplex, this port is full duplex, full duplex, full duplex, full duplex. So how many collision domains we will have?
Would we have none?
We will have 4.
Okay,
So
4. Okay.
let's see why. If this is full duplex and this is full duplex, they will work in full duplex. What does it mean, full duplex? That out of the 4 pairs that we have, we will use 1 pair to send, 1 pair to receive, which means that switch 1, when it's sent to switch 2, use 1 of the 4 pair, and switch 2, when it's sent to switch 1, use another pair. So there will never be collision here. So they can, switch 1 can send to switch 2 and switch 2 to switch 1 at the same time. So there is never collision in this link. Now what will happen here? The hub is always half duplex, which means that the hub only use 1 pair. The switch is new. It can use 2 pairs, 1 to send, 1 to receive, or just 1 pair. When it uses 1 pair, it send and receive in this pair of cable. So the switch is more intelligent than the hub. It will realize that the hub only supports 1 pair, which is half duplex. So the switch will put this interface in half duplex. If it puts this interface in half duplex, this will be 1 collision domain. So here we can have 1 collision, which means that between these 3 PC and the switch in this interface, only 1 can transmit at the time. Otherwise, we will have a collision. So we have 1 collision domain here, another collision domain here, a 3rd collision domain here, and a 4th collision domain here. And here we don't have collision. So the number of collision domain is 4 in this case. Okay, D say, if the port of the switch are full duplex, which means I have new switches, modern switches, what is the number of broadcast domain? So the number of broadcast domain, if there is no router, will be 1. Remember that to have different broadcast domain, we need routers. And each interface of a router is a different broadcast domain. So here we have just 1 broadcast domain. Okay, which means that if this PC transmits a broadcast, this 3 PC and this 8 PC will receive it. Okay, because there is only 1 broadcast domain. All the devices that are in the network will receive the broadcast. Question 86, refer to the exhibit. If the port of the switch are half duplex, we have an old switch. What is the number of collision domain? So if we have an old switch, so the PC can be new or old. But if the PC is new, it will realize that the switch is old. So the PC will put its interface in half duplex if it is new. If it is old, it will be in half duplex from the beginning. So at the end, if this size is half duplex, This size have to be half duplex also. So here we will have half duplex. What does it mean? If both sides are half duplex,
Then we can have a collision.
we have one collision domain, which means that between this PC and this interface of the switch, only one can transmit at the time. If the PC transmits, the switch cannot be transmitting in this interface. If the switch is transmitting on this interface, the PC cannot be transmitting. Otherwise, we have a collision. So we will have a collision domain here between this interface of the switch and the PC. We'll have another collision domain here between this PC and this interface. We'll have a third collision domain here between this PC and this interface. Now, the hub is only one collision domain. So all this interface and this 3PC, all this will be another collision domain, which means that we will have 1, 2, 3, 4 collision domains if the switch is old. Now let's see this question. If the switch is new and support full duplex, how many collision domains we will have? So
Just
the switch, we'll have 3. So the switch is new. It can put this interface in half duplex or full duplex. It will put it in what? What do you think? So it's connecting to a hub. A hub always have the interface in half duplex. So of course this link, if one side is half duplex, the other side have to be half duplex. You cannot have mismatch. So the hub only supports half duplex. So the switch, which is modern and more intelligent, will put this interface in half duplex. So all on the PC here will put, if they are intelligent, if they are modern, they will also put their interface in half duplex. If they are old, the interface is already in half duplex. So all this will be one collision domain. Now the switch is modern. They ask what will happen. So if this PC is modern, they will put, both of them will put their interface in full duplex. If their interface is in full duplex, there will be no collision between in this link. So it will depend if the PC are modern or not. Now, if you put an old PC here and 2 modern here we will have a collision domain, and here we will have no collision, and here we will have no collision, because the switch is modern and the PC is modern. Okay, so modern devices are intelligent and they are able to put their interface in half duplex or in full duplex. They will put it in half duplex if the other side only supports half duplex. But if the other side supports full duplex, we will work in full duplex. We always work with the best possibility. So if both will support full duplex, we both will use full duplex. If only one side supports full duplex and the other side supports half duplex, the side that is intelligent will adapt its interface in half duplex. And if both are half duplex, well, both are half duplex, no? So, okay, let's see this question now. If the switch is old, how many broadcast domains we have? So the number of broadcast domain will not depend of if the switch is old or new. There is only one broadcast domain here because we don't have router. Okay, so if this guy send a broadcast, all the other PC receive it. If this guy send a broadcast, these 2 PC and this 3 PC will receive it. Question 87, refer to the exhibit. If the port of the switch, we have a switch here, are half duplex, all switch, what is the number of collision domain? So if I am half duplex, the router can be new or old. But if I am half duplex, the router, if it is new, will put this one in half duplex. If both are half duplex, we have a collision domain here, which means that If the switch sends something to the router, and the router sends something to the switch, we will have a collision. Okay, so if this is half duplex, this one has to be a half duplex. If this is half duplex, and you put a new PC, the PC is going to put this interface in half duplex. If you are an old PC, it is already in half duplex. So what does it mean? One collision domain here, one collision domain here, one collision domain here, one collision domain here. Already 4 on this side. What about this side? All this will be one collision domain. It doesn't matter if the router is new or the PC is new, because this guy is old. All these interfaces will be in half duplex, which means that if the router is new, the router will adapt its interface to work in half duplex because this guy is old. If the PC is new, it's connecting to an old hub, it will adapt its interface to work in half duplex. So at the end, all this will be one broadcast domain. So we will have 1, 2, 3, 4 broadcast domains. Now, look at what they say. If the switch is new, the router and the PC are new, what will be the number of broadcast domain? So router is new, switch is new, and PC are new. They support full duplex. How many broadcast domain we will have? So let's see this link. I support both. I am the PC, I support both. The switch support both. So when we negotiate, we will negotiate what? Full duplex. We always work with the best case. If we negotiate full duplex, there is no collision. Full duplex, we use one link to send, one different link to receive. One pair to send, one pair to receive. So no collision here, no collision here, no collision here. If the router is new, the switch is new, this interface supports full duplex, this interface supports full duplex. So this link will go full duplex, no collision. One pair of link for the router to send, one pair of link for the one pair of wire for the switch to send. So no collision. The hub is always old. The hub have half duplex, half duplex, half duplex, half duplex. So these guys support both the PC, but you see that is connecting to a device that only supports half duplex. Since we cannot have mismatch, it will put this interface in half duplex. So we will have this link will be half duplex. This one also, this one also, this one also, which makes that all this will be one collision domain. So in this case, C, we will have one collision domain that will include this 3PC and this interface of the router, which means that if the router transmits on this interface, these 3PC have to wait. They cannot transmit at the same time. If this PC transmit on this, if this PC transmit, these 2 PC on the router have to wait. They cannot transmit at the same time. Otherwise, we will have a collision. Now, number of broadcasts. We have 2 broadcast domains. This will be one broadcast domain. This will be another broadcast domain. It doesn't depend if the devices are new or old. Each interface of a router is a different broadcast domain. So one broadcast domain here, one broadcast domain here. Which means that is this PC send a broadcast, this PC get a copy, and the router, because of this interface, get a copy. Okay, if the router on this interface send a broadcast, these 3 PC get a copy because they belong to the same broadcast domain. Okay. Let's pass this exercise. Let's go to the other one. I want to see the other one. Okay. Look, those are very interesting exercises, and it's where we are going to learn what is going on in a network. So let's see. The following figure shows the interconnection between 7 PCs. PC1, PC2, PC3, PC4, PC5, PC6, and PC7 through one switch. The MAC address of the PC are specified. So to make it easy, the MAC address of PC1 is M1. The MAC address of PC2 is M2. Okay, the MAC address of PCI is MI. Okay, we make it easy. We are not going to say the MAC address is 00 colon F3 colon, it's too long to say. So we just say PC4, MAC 4, PC5, MAC 5, okay? But you know that the MAC address is 48 bits. So it's something like 00 colon 20 colon AC colon, it's long to say, as you can see, no? Okay, question 1. For the proposed network, give the number of collision domain and the number of broadcast domain. So, number of broadcast domain. 1. We don't have router. If we don't have router, we cannot have more than 1. If we have router, each interface of the router will be a different broadcast domain. Which means that if PC6 send a broadcast, all the other PC receive a copy of the broadcast. Okay, number of collision domain. Let's say that the switch is old. If the switch is old, how many collision domain I will have?
Would it be 7?
Correct. Because if the switch is old, all these interfaces will be half duplex. So it doesn't matter the kind of PC that I connect. If it's old, it will be half duplex. It's a new, it will have to put the interface in half duplex. So we are going to work half duplex. If we are going to half duplex, we will have one collision domain here, another here, another here, another here, another here, another here, and another here. Now, if the switch is modern, it supports full duplex. Let's say that all the PC also are modern. They support full duplex, which means that this link will go full duplex because both devices that are connected in this link support full duplex. So no collision here, no collision here, no collision, no collision, no collision, no collision, no collision. So if all the devices are modern, there is no collision. This is what is happening today. All the devices are modern. There is no collision anymore. Now let's say that all those are modern, but these two are old. How many collision domain I will have?
2.
2. One here and one here. Okay? Okay, so assume that the network is in its initial state. That is, no traffic have been generated. So I just put all the devices on. Okay, now 7 frames are sent. The first frame is a unicast from PC2 to PC3. So PC2 send it for PC3. The second frame, it is there. Unicast from PC2 to PC3. The second frame is a unicast from PC4 to PC5. So PC4 want to send something to PC5. This is the second frame, okay? So all the 7 are specified. If you look at this, second, third, fourth, fifth, the 6th frame is a broadcast. So if we read here, the 6th frame is a layer 2 broadcast. So PC5 want to send it to all the others. So PC5 want to send it to PC1, PC2, PC3, PC4, PC6, and PC7. And the last frame is also a broadcast. The source is PC1, and of course, the destination has to be all the other PCs. Okay, so they say, for each frame, each of this frame, we are interested in the incoming port, the port where the frame enter, the switch. The outgoing ports or the outgoing interfaces, the ports where the frame is going to be copied. The action taken by the switch when learning. So a switch can add a new entry if it didn't have, or if the entry was already there, the switch is going to update the entry as we saw in class, no? Okay, and the action taken by the switch when forwarding the frame. So a switch can do one action of 3. Commutation is when you receive on one port and you send on a different port. For example, if the switch receive from PC1 on port E7 and send it to PC3 on port E5, that will be commutation. Flooding is when you receive on one port and you copy in all the other ports. So what will be, for example, let's say that PC1 sends something to the switch. It enters the interface E7 of the switch. If the switch do flooding, the switch will copy to PC6, it will copy to PC2, to PC3, to PC4, to PC5, and to PC7. So flooding is there is one incoming port or one incoming interface, and all the other interfaces are outgoing port. I copy it through all the other interfaces. And filtering is I receive a frame on one interface, I am the switch, and I drop it. I don't forward it at all. So commutation, I send it, I receive on one port, I send it on another port. Flooding, I receive on one port and I copy to all the other ports. Filtering, I receive on one port and I drop it. Okay, so you have to say the action of learning, the action of forwarding, and the list of PC that receive a copy of the frame. Okay, so to make it easier, let me, since we have all the information here, let me do that. So we can see all. Let me do that. And here, what is the difference between a switch and a hub? That the switch is more intelligent and can do commutation, flooding, or filtering. The hub only do one thing, flooding. This is one difference. The hub always copy what it receives on one interface to all the other interfaces. The switch is more intelligent because you have, in memory, it maintains a table, which is called the CAM table. So this table that is there is a table that we will be filling. Let's see what will happen. PC2 wants to send something to PC3. So it will send a frame. What will be the destination MAC address of this frame? We are talking about we are doing the first one. M3, correct. What will be the source MAC address? M2, correct. So look, PC2 send it. The frame enter which interface of the switch? E9. So the incoming port or the incoming interface is going to be E9. Okay? Now, let's see the learning. The CAM table of the switch is empty. How do the switch, if you remember the class, the lecture that we have, the switch learn with which MAC? The source or the destination MAC address of the frame? It learns with the source MAC. So the source MAC of this frame is M2. So the switch look at here. Do I have an entry already for M2?
No.
No. So the switch is going to say, oh, I'm going to add an entry for M2. I know that the device with MAC M2 is connected on my interface E9. Why on my interface E9? Because the frame enters my interface E9. So the switch will learn that. So what is important here? That in the future, if the switch has something for PC2, it's already know that PC2 is connected on E9. He already learned that the device with MAC address M2, which is PC2, is connected on E9. So he learns something from this transmission. So the learning action will be add entry for MAC2. Okay? It will add an entry for MAC2. Okay. Now that the switch have learned, the switch will take a decision what to do with the frame. So the switch can do commutation, flooding, or filtering. So how the switch take a decision? So if you remember the lecture, we say that if the destination MAC address of the frame is a broadcast address, which is FF:FF:FF 6 times, the switch will do flooding. Now, if the destination MAC address is a unicast address, and I have an entry in my CAM table for this destination MAC address, which means that I already know where is the device, I will do commutation because I already know where it is. Now, if I don't know where is the device, what do you think we should do? Okay, there is no MAC address in the port of a switch. Who have MAC address? The PCs. On the network interface card, they have MAC address. The PC don't have MAC address. The switch don't have MAC address. So in this case, for example, PC2 is sending something to PC3. So the switch up to now doesn't know where is PC3. Why it doesn't know? If it look at its MAC address table, there is no entry for M3. There is an entry for M2 because it just learned it. But the switch doesn't know where is M3, doesn't know where is PC3. What do you think the switch should do if it doesn't know where is PC3? To be sure that PC3 get a copy.
Flood.
Of course, it will do flooding. Because if it copy it everywhere, he is sure PC3 will be connected in one part. I don't know where it is connecting, so I send it everywhere to be sure PC3 get a copy, because I don't know where it is. So what action it will do? Flooding. And if you do flooding, what will be the outgoing port? So it enter E9. Flooding is when I copy it to all the other ports. So what will be the outgoing port? E1 will be an outgoing port. What else? E7 will be an outgoing port. E5 will be an outgoing port. E3 will be an outgoing port. E4 and E2, all the other ports. So it enter E9, and I do flooding because I don't know where is PC3. I want to be sure PC3 receive a copy. So I do flooding. So I send it on E1, I send it on E7, I send it on E5, I send it on E3, on E4, and E2. So who receive a copy? When I send it on E1, PC6 receive a copy. So Was PC6 the destination? In the intended destination? No. The destination really is PC3. So PC6 will drop the frame. It will look at the destination MAC address. It will say, oh, the destination MAC address is M3. This is not mine. My MAC address is M6. So this frame is not for me, I will drop it. This is what PC6 will do. So when you send it out E7, who receive a copy? PC1. PC1 will drop it also. Who else receive a copy? PC3. Now PC3 will process it because the destination MAC is M3. PC3 see, oh, this is my MAC address. This is for me. I have to process it. Bingo, this is what we want. We want PC3 to receive a copy and to process it. Now PC4 will also receive a copy and will drop it. PC5 will also receive a copy and will drop it. PC7 will also receive a copy and will drop it. So you see with this first frame that PC2 sent to PC3, the switch learned that PC2 is connected on E9. So the switch is a little more intelligent than at the beginning because it already knows that PC2 is there. Let's see the other frame, the second frame. PC4 sent to PC5. What will be the destination MAC?
M5.
Correct, M5. What will be the source MAC? M4. Okay, so PC5 is here. What will be the incoming port? E4. So the port where the frame enter is E4. So let's see what the switch will do at the learning level. You look at the source MAC. The source MAC is M4. PC4, oh, so PC4 is here. So the incoming port will be E3, no? PC4 is here, no? So the incoming port will be E3. So the frame enter here. So first the switch is going to learn. So you look at the source MAC. The source MAC is M4. Do I have an entry here for M4? No. So I'm going to add a new entry. I'm going to say M4 is connected to port E3. So from now on, if I receive something for PC4, I know that it's connected on the interface E3. On this entry, normally the switch put them for 5 minutes. So if they are not renewed, they will disappear. They will be removed. So there is normally another entry, which is the timeout. So each entry is put for a certain amount of time. So the switch just learned something. It just learned that PC4 is connected on E3. Now the switch is going to take a decision what to do with the frame. So it look at the frame and you see that the destination MAC is M5. Does the switch know already where the device with MAC M5 is connected to it? No, there is no entry with M5, so it doesn't know where is PC5. So what should do the switch?
Should flood.
It should do flooding, so it's going to do flooding. So flooding will mean that the frame enter E3 and will be sending all the other ports, so E1, E7, E9, E5, E4, and E2. So it will be sent out E1, E7, E9, E3, E5, 4, 2. Okay, when the switch send it on E1, who receive a copy? PC6. I should do PC6 with this frame. So PC6, look at the destination MAC. The destination MAC is M5. This is not the MAC of PC6. So PC6 drop the frame. Okay, when the switch copy the frame on E7, who receive a copy? PC1. He dropped the frame also. Who else receive a copy? PC2. PC2 dropped the frame. Who else receive a copy? PC3. PC3 dropped the frame. Who else receive a copy? PC5. Bingo. PC5 process the frame. Who has received a copy? PC7. PC7 dropped the frame. So here I forgot to write it, but we add an entry for M4. We learned that PC4 is connected on E3. Let's see the third frame. PC1 sent a frame to PC2. That is here. So what will be the destination MAC? M2. What will be the source MAC? M1. So the frame enter E7. So let's put incoming port E7. So the switch first learn. So the source MAC is M1. Do I already have an entry for M1 in my chem table? No. So I'm going to add an entry for M1. And I'm going to say M1 is connected on interface E7. So I learn what it's doing at the level of learning is adding an entry for M1. Now the switch look the destination MAC. M2. So I need to reach PC2. Do I already know where PC2 is connected to me?
Yes.
Yes. We have this entry, the first entry. The first entry say, okay, the first entry say that if you want to reach the device with MAC M2, it is connected on interface E9. So what should do the switch?
Commutation.
Correct. It will do commutation. Commutation, if you remember, is that I receive on one interface, in this case E7, and I will send it back only on one interface. On which interface? In this case E9. Because I already know where is PC2. I already know where is the device with MAC M2. Okay? So the outgoing interface is going to be E9. Who is receiving a copy? Only PC2. This is a good thing that after some time, the switch know everything. And instead of doing flooding, like the hub do always flooding, the switch do commutation. So this time it did commutation. So of course, when it arrived to PC2, PC2 look at the destination MAC address, M2, this is MAC. So PC2 will process the frame. Bingo, this is what we want. Let's see the next one. PC2, this device send something to PC4. You want to send something to this device. So in the frame, the destination MAC will be M4. The source MAC will be M2. So the frame enter which interface in the switch? E9. So E9 is the incoming interface. So the switch take a decision about learning. So he look at the source MAC of the frame, M2. Do I already have an entry for M2? Yes.
Yes.
So what should I do?
Refresh.
Exactly, I refresh the entry. I refresh it. You're right, refresh. Oh yeah, that's right, yeah. Refresh. Or update the entry. So it will update the entry of M2. So this entry have been there for a certain amount of time. So it was, they put, I think it's 300 seconds or 500, no, 300 seconds, which is 5 minutes, yeah. So it was going down and it put it again 300 seconds. It say, oh, since PC2 just confirmed that it is there and it is alive, let me give this entry another 300 seconds. So it refreshed the entry, okay? Okay, so it didn't learn because the entry was there, it just refreshed the entry. So now it's look at the destination MAC of the frame, M4. Do I know where the device with MAC M4 is connected to me? So I look at my CAM table. Do I have an entry for M4?
Yes.
Yes, I have an entry. The second entry say that if I want to reach M4, I have to go out E3. So I will go out E3, which means that I will do what? Commutation. I will just send it out one interface. And if I send it out E3, who received the frame? Just, this is what we want. We want just PC4 to receive the frame. We did commutation. Let's see the next frame. PC7, which is this guy, sends something to PC2. So the destination MAC is going to be M2. The source MAC is going to be M7. So since PC7 sent it, the incoming port will be E2. So it enters the port E2 of the switch. So the switch look if it can learn something. So it look at the source MAC. The source MAC is M7. Do I have an entry for M7 up to now? No. So I add, and I say, okay, next time that I need to reach a device with MAC M7, which is PC7, it is connected on my E2 port. And I give this entry 300 seconds of life. So during 300 seconds, I know that the device with MAC M7, which is PC7, is on E2, on my interface E2. Okay, so now I take a decision what to do with the frame. So I look at the destination MAC, M2. Do I already know where is M2? A device with MAC M2?
Yes.
Yes, because I have an entry here. So this entry says send it out E9. So I will send it out E9, which means that I will do commutation. So by sending it out E9, who receive a copy? PC2, bingo, because this is the intended destination. Okay? Okay, here I forgot to put that I add an entry for M7, no? Okay, look at this frame, it's a broadcast. Who sent this frame? PC5. So what will be the destination MAC? FF colon FF colon FF colon 6 times. This is the MAC address for broadcast. Okay, what will be the source MAC? M5. So this frame will enter E4. So I write here, it enter E4. So the switch look at the source MAC to learn M5. Do I have already an entry for M5? No. So I add an entry saying that next time that I need to send something to a device with MAC M5, it is connected on E4. So here we add an entry, we learn something, and we put 300 seconds for this entry. We add an entry for M5. Now, the switch takes a decision if it's going to do filtering, flooding, or commutation. For that, it looks the destination MAC. The destination MAC is FF colon FF colon FF 6 times. When the destination MAC is the broadcast MAC, the switch always do flooding because this is a broadcast. A broadcast is for everybody. Since it's for everybody, the switch in the case of a broadcast have to do flooding. So the switch will do flooding. By doing flooding, it's enter E4, it will be copied in E1, it will be copied in E7, in E9, in E5, in E3, and in E2. Who receive a copy? PC6, bingo, because PC6 should receive a copy, it's a broadcast. Who else receive a copy? PC1, bingo. Who else receive a copy? PC2, bingo. You have to receive a copy and process it. PC3, good also. That PC3 receive a copy. PC4, good also. And PC7, good also. So the PC normally will process frame that arrive with their MAC or the broadcast MAC. The broadcast means everybody have to process it. So if the destination MAC is the broadcast, they will process. So all of them will process. And that was the objective of PC5. PC5 want everybody to process it. And we have a last frame sent by PC1, and it's a broadcast frame. So the destination MAC is FF colon FF 6 times. The source MAC is M1. Okay, so this frame will enter E7, the interface E7 of the switch. So the switch will look at the source MAC to learn. M1. Do I already have an entry for M1? Yes.
Yes.
What should I do? Refresh this entry. So this entry was there for a certain amount of time. I put this entry to 300 seconds again. So I refresh M1. I refresh this entry, saying that, okay, the device with MAC M1 that is connected on E7 just told me that it was still alive. So let me give it another 300 seconds to be there, because it just shows sign of life. Okay, so now the switch look at the destination MAC to see what it's going to do. So it's going to do flooding, filtering, or commutation. The destination MAC is FF colon 6 times. It's a broadcast. Every time that it's a broadcast, the switch do flooding. By doing flooding, it enter E7. It will copy it in all the other interface. So E1, E9, 5, E3, E4, on E2. Who receive a copy? When you send it on E1, PC6, bingo. It's a broadcast, PC6 need a copy. Who else receive a copy? PC2, bingo. PC3, good. PC4, good. PC5, good. And PC7, good. So you see how it's work? Because I have a CAM table, I'm able to learn who is connected to my interfaces. So when I need to contact this device, if I have an entry, I already know where is this device. So if this was a hub always do flooding. A hub cannot do commutation. A hub cannot do filtering. Always do flooding. So if you remember this, we saw that in class. It was some time ago, but I'm going to go back and show you that we saw that in class. Maybe this one. Yes, this one. Look at this table. This say everything. Learning process. The switch examines all incoming frame for new source MAC address information to learn. So if the source MAC address is unknown, which means that it is not in the CAM table, it will add in the table, it will add this MAC address in the table with the incoming port. So it will add a new entry and it will set a timer for this new entry in 300 seconds. Now, if the source MAC address does exist, the switch will just update or refresh the timer for this entry in the table, put it in 300 seconds again. So by default, most of the switch have a timer of 300 seconds. Okay, look at now the forwarding decision. If the MAC address is the broadcast address, which is FF, FF, FF 6 times, the frame is flooding all the time because it's a broadcast. A broadcast is for everybody. So it enters one port, I flood it out all the other port. Otherwise, if the MAC address is a unicast, the switch look for this MAC address in the CAM table to see, oh, let me see if I already know where is the destination. So if I don't know where is the destination, which means that I look at the MAC address table and the destination MAC, I don't know where it is. So the switch will do flooding. Because I don't know where it is, I send it out everywhere to be sure the destination receive a copy. Now, if the switch do find the MAC address in the CAM table, it will forward the frame only on the port that is specified by the entry. So there is something that that they say here that we didn't see. If I receive on one port and the CAM table tell me send it back on the same port, I do filtering. We didn't do in this exercise, there were no filtering. So we'll do filtering if I receive it on one port, I know where is the destination. And the destination is in the same port where I receive the frame, I don't send it back. I drop it. Now, if I receive it on one port, and the CAM table say you have to send it in another port, I do commutation. Okay, so we can have filtering. This exercise didn't have filtering, but other exercise that we will see next week will have filtering. Okay, so try to do this exercise. Here we have filtering. Try to do, here we have a switch, here we have a hub. So remember, a hub doesn't have a CAM table. Always do flooding, not intelligent at all. A switch do have a CAM table. This is the CAM table of the switch. And the switch learn. And the switch is able to do commutation, filtering, or flooding. The hub only do flooding. Only. What I receive on one port, I copy it in the other ports. I am not intelligent. I'm an old device. At the beginning, we only have hub. Then we invent the switch. But at the beginning, everything was hub. Now they don't do hub anymore. You have to buy a second-hand hub on eBay if you want a hub. Or you can configure a switch and say that with all these ports, you want to create a small hub. So you can still do it with a switch by configuration. No? Okay, so try to do this exercise. This exercise that involves two switches. So you have a CAM table for switch 1 and a different CAM table for switch 2. So if you look here, CAM table for switch 1, CAM table for switch 2. Then try to do this one. We have 3 switches. So one CAM table for switch 1, one CAM table for switch 2, one CAM table for switch 3. You have 3 CAM tables, as you can see, no? Here we have 2 switches on a hub. Flooding all the way here. CAM table, CAM table. Switch 1 and switch 2 both have CAM table. So you will have CAM table of switch 1, CAM table of switch 2. Hub don't have a CAM table. Hub, switch. This guy have a CAM table, no CAM table, no CAM table. Okay, so just one CAM table, as you can see. Router, switch. CAM table, CAM table, CAM table, CAM table, CAM table. 5 CAM table. Routing table. A switch have a CAM table, a router have a routing table. So of course, you will have 5 CAM tables, as you can see, no? And remember that the router have routing table. Here we have only routers, so we have 6 routing table. Each router have its own routing table. Okay, remember that next week, from today, in 1 week, we have quiz number 2. Okay, be ready for quiz number 2. Okay. I will see you on Tuesday.